Okay. So, for this course, this is the last topic, and the title of this is power system stability. Whatever, and here we will mainly will see the transient stability for single machine infinite bus system, but before that we will see something more regarding some description of your steady state stability, dynamic or small signal stability, and some kind of mathematical derivation and understanding. And power system stability actually that implies that its ability to maintain to return to normal or stable operation after having been subject to some form of disturbance. That means, you give some disturbance, and if it comes back to its after some kind of your what you call, it will deviate from its or what you call from its original steady state point, but after some time if it returns very to the stable point or very close to that, that means we call that system is stable, right. So, actually in a power system you will find that there is always a disturbance, because some loads are switching on, some loads are switched off, but systems are always stable. I mean, this kind of disturbance is very small or what you call for this is no, I will not say small disturbances, but this kind of disturbance always is on in power system, but our system remains stable. So, that is why that power and your power system stability, that is why implies that is ability to return to normal or stable operation after having been subjected to some form of disturbance. So, what kind of disturbance, that we will see later, but in power system that disturbance is always on, which like because some lights are switched on, fans are switched off, something like that, and some loads are switched on, switched off, it is a continuous process. So, and instability means a condition denoting loss of synchronism of synchronous machine or falling out of step, that is instability. Actually, stability itself is a huge course or huge thing, but we will restrict to as far as this course is concerned at undergraduate level. So, therefore, the state of equilibrium or stability of a power system commonly alludes to maintaining synchronous operation of the system, right. So, that means you have to maintain the stability of power system. So, we will focus on this aspect of stability, that whereby a loss of synchronism will mean to render the system unstable. So, synchronous machine will never lose synchronism and will not fall out of step, and system will remain stable. So, when we define stability of the power system, there are only three types of stability actually are generally are of concern. One is steady state one, another one dynamic or called small signal stability, and last one is the transient stability. So, of course, many other stabilities are there in power system that is beyond the scope, for example, voltage stability. So, steady state stability relates to the response of a synchronous machine of a gradually increasing load, that you increase the load gradually, and you can find out that determines the upper limit of the machine before it losing synchronism. That means, stability, the steady state stability relates to the response of a synchronous machine to a gradually increasing load. It is basically concerned with the determination of the upper limit of the machine loadings before losing synchronism, provided the loading is increased gradually. So, gradually your loading is getting increased, but at up to it will sustain up to a maximum limit. After that, it may fall out of your step, that is it may lose synchronism, right. So, and dynamic or small signal stability actually it involves the response to small disturbances that occur in the system, producing oscillations. That means, because of small disturbance there will be a continuous oscillation. So, the system is said to be dynamically stable if these oscillations do not occur more than certain amplitude and die out quickly, but if their oscillations continuously grow in amplitude, the system is dynamically unstable. Actually, the small signal stability, it involves huge analysis. We will not study this one. It is huge. It involves huge analysis for synchronous machine, and to damp out this your what you call this oscillation, if there is a small disturbance, say some step increase in mechanical torque some form, and there will be continuous oscillation, and to damp out those oscillations, but in that omega, that is in that case commonly used thing is that power system stabilizer. So, lead lag stabilizer. So, those things we will not study for small signal stability analysis, but for this case you need that your what you call that detailed analysis of synchronous machine, particular dynamics. And another one is the transient stability. It involves the response to large disturbances that you know, which may cause rather large changes in rotor speed, power angles and power transfer, but transient stability is a fast phenomena and usually evident within a few seconds. So, but among this, the transient stability of course is very severe, because it is due to a large disturbance, means suppose there is a fault, 3-phase fault or line to ground fault. In that case, your what you call it rather your what you call it will be large change in the rotor speed, power angles and power transfer. For example, a double circuit line, there is a fault in one line. So, naturally power transfer capability will change, and those kind of your what you call that large disturbances, it cause transient that phenomena is called transient stability. So, in that case your what you call it is basically within a few seconds. So, that means if such fault is occurred, you have to see the fault is cleared in very quickly, right? Maybe 4 cycles or 6 cycles, the fault has to be cleared. So, these are the 3 different type of faults. One is I told you that not fault, steady state stability, then 3 types of stability, then small signal or dynamic stability, and then transient stability. But our concern for this course will be transient stability and generally single machine infinite bus system. So, inertia constant and the swing equation. The swing equation, that is that they describe the dynamics of the rotor of synchronous machine. So, inertia constant and the swing equation. So, inertia constant and the angular momentum, it plays an important role in determining the transient stability of a synchronous machine. So, the power unit inertia constant H, actually it is we are calling power unit inertia constant H, but later we will see its dimension is megajoule MVA per MVA, or it is can be given a unit in second also. Is defined as the kinetic energy stored in the rotating parts of the machine at synchronous speed per MVA rating of the machine, that is we define the inertia constant. So, now the rotor kinetic energy at synchronous speed is given as that kinetic energy K E we define half J omega S, it is mechanical speed, right, synchronous speed mechanical omega S square into 10 to the power minus 6 megajoule. So, J is moment of inertia actually in kg meter square, and omega S square is mechanical speed, but I will come to that, and where J is equal to moment of inertia of rotor kg meter square, omega S mechanical is synchronous speed in mechanical radian per second, and you know the relationship that we know the relationship, that is your theta electrical is equal to p by 2 theta mechanical, this we know. So, same philosophy, that omega S electrical is equal to p by 2 omega S mechanical, that is rotor speed in electrical radian per second, but if p is equal to 2, the 2 pole machine, then omega S electrical is equal to omega S mechanical, and p is equal to number of poles of machine. Now, from equation 1 and 2, that means this equation, if you replace omega S mechanical by omega S electrical, then it will become kinetic energy will half J into 2 by p square whole square into omega S electrical into 10 to the power minus 6, that is into your omega S electrical. That means kinetic energy also you can write that half m into omega S electrical, that means this portion we are defining as m. This is say equation 3, where where m is equal to j into 2 by p whole square, omega is electrical into 10 to the power minus 6, that is moment of inertia in megajoule second per electrical radian. This is that unit of this your what you call the same is moment of inertia in megajoule second per electrical radian. This is equation 4. Now, we shall define the inertia constant H such that you define inertia constant H such that G into H is equal to kinetic energy is equal to half m omega s electrical radian, electrical, that is not radian, omega s electrical, say this is megajoule. So, we are defining G H is equal to actually kinetic energy half m omega s electrical, this is in terms of megajoule. Wherever possible I have written the unit, there will be no confusion then. Where G is equal to 3 phase MVA rating, that is the of machine, it is a base value, and H is equal to inertia constant in megajoule per MVA or megawatt second or second. Actually, if it is your megajoule per MVA, say you know that your what you call joule per second is equal to watt. That means, joule is equal to, I am writing in simply short form, joule is equal to your watt second, that means megajoule is equal to megawatt second. That means, this one can be written as megawatt second slash MVA. So, MVA megawatt by MVA, it is a dimensionless quantity, that means H can be defined that is in second also, right. So, if you read some book, you will find inertia constant H is given as a second, actually it is megawatt second per MVA. So, it is actually MVA megawatt MVA is dimensionless. So, it is given in second. So, your that is why H inertia constant in megajoule per MVA, I told you it is or it is megawatt second per MVA or it is second. Next is that from equation 5, from this one. So, you can write that m is equal to 2 g h upon omega s electrical is equal to, you can write 2 g h upon 2 pi f, omega s is actually omega is equal to 2 pi f. So, writing omega s electrical is equal to 2 pi f. Now, m is equal to whatever I showed you here, I have made it here also, that megajoule is equal to megawatt second, we will come to that later on. So, m is equal to g h upon pi f, 2 will be cancelled, it is megajoule second per electrical radian, that is your m. Now, or if you want in degree, then instead of radian pi you can put at 180, right. So, m is equal to g h upon 180 f, that is megajoule second per electrical degree. It is in radian if it is a pi, if it is 180 it is electrical degree. This is equation 7. M is also called the inertia constant. So, that means assuming G as a base, the inertia constant in per unit is m pu is equal to m per unit, actually it is m per unit is equal to h upon pi f. That means that your m is equal to g h upon say pi f. If you divide both sides, that G actually G is that your, I have told you that 3 phase MVA rating, that is the base of the machine. So, if you divide by G on both sides, that is m by G is equal to your h of pi f. That means, this one we can put m per unit is equal to h by pi f. So, that is why that your m is your what you call that m is also called the inertia constant, and assuming G as a base, I showed you the inertia constant in per unit m p is h upon pi f, that is second square by electrical radian, because this is megajoule second and megajoule is equal to actually your megawatt second. So, if you replace this your what you call the dimension wise, if you replace like this, that just hold on, dimension wise if you replace that megajoule second, then electrical degree, but megajoule is equal to megawatt second. If you put is megawatt second, it will be megawatt second square, that will be your megawatt second square per electrical degree. Now, as this is the original unit, but if both side when you divide by its machine base g, in that case the unit of this thing coming second square per electrical radian, or your what you call the way you want, this is per electrical radian, and this will be, if you want this one, it will be second square per electrical degree. I have written here second square per electrical degree, because megajoule is equal to megawatt second. So, if you put here, it will be megawatt second square per electrical degree, and both side if you divide by g, it will be a per unit, and this side, and ultimately megawatt per MVA is a dimensionless. So, ultimately unit will be your second square, either second square per electrical degree, or if you want a radian, it will be second square per electrical radian. So, that is why m per unit is h upon pi f, and its unit is second square per electrical radian. This way it can be defined. So, there should not be any confusion for particularly the unit. Little bit you practice, then absolutely there is no problem. So, therefore, if we write in degree, then MPU is equal to h upon 180 f second square per electrical degree. This is equation 9. Now, we will come to your slowly and slowly we will come to this swing equation other thing. So, now figure 1 actually flow of powers in a this is a generator. So, consider a synchronous generator as shown in figure 1, right, developing an electromagnetic torque T, right, and a corresponding electromagnetic power P, this is P, while operating at the synchronous speed omega s. So, before telling this, what we will do? We will assume windage, friction and iron loss torque is all negligible. All these things, any such thing is negligible. We will not consider for our study. These all will be neglected. So, if the input torque provided by the prime mover, I mean if the input torque provided, this is your input torque provided by the prime mover at the generating shaft, that is T I, this is the input torque, this is the input torque, then under steady state condition, that is without any disturbance, that T must be is equal to T I. We are assuming all losses, everything is neglected. So, T will be is equal to then T I. So, that is without any, and it is a steady state condition. Now, if you multiply both sides of this equation by omega s, the synchronous speed. So, that is why here I am writing also, here we have neglected any retarding torque due to rotational losses. So, if you multiply both sides this equation by omega s, it will be T omega s is equal to T I omega s. That means, this equation actually you know that your power is equal to torque into angular speed, that you know. So, that means that T I omega s, putting this first, minus T omega s is equal to, we can write it is power, this is P I actually, P I is equal to T I omega s, and this is P is equal to T omega s is equal to P I minus P is equal to 0. This is 0 when system is at your steady state condition, that is this is equation 12. So, now if there is a departure from the steady state occurs, for example, a change in load or a fault, this is a perfect condition at steady state say, and if there is a departure from steady state occurs, for example, a change in load or a fault, the input power P I actually is not equal to your P, that means that input power this P I is not equal to P. I have taken here input power P I, some article book they are considering this as a P M, but I have taken it as an input power P I. So, the input power P I is not equal to that your P. So, therefore, the left side of equation 12 is not 0, that means this P I minus P actually it is not 0. So, and an acceleration torque comes to play. So, if P A is the accelerating, P A is the corresponding accelerating power, accelerating or decelerating, then this P I minus P E can be written as m into d square theta e dt square plus d into d theta e upon d theta is equal to P A. P A actually is equal to P I minus P, that accelerating or decelerating power. We will come to that later on. So, m we have seen, m has been defined in equation 8 or equation 9, d is the damping coefficient and theta e is the electrical angular position of the rotor. First we will write like this way, although later we will assume that d is equal to 0 for this your study. So, it is more convenient to measure the angular rather than this one, more convenient to measure the angular position of the rotor with respect to a synchronously rotating your frame of reference or rotating reference frame, synchronously rotating reference frame. So, that is better, more convenient to measure. For even for stability studies we do so. That means if it is if we your measure the angular position with respect to synchronously rotating your reference frame, that means your delta we define is equal to say theta e minus omega s into t, right, with respect to synchronously rotating reference frame, that is omega s into t. And if you take the double derivative of this equation 14, you will get d square delta dt square is equal to d square theta e dt square, or other way you can write d square theta e dt square is equal to d square delta dt square. This is say equation 15, and where delta is the power angle of the synchronous machine, sometimes we call torque angle also, right. So, neglecting damping, your that is d is equal to 0, and substituting equation 15 in equation 13, then what we will get in this equation, you put d is equal to 0. So, and this d square theta e dt square you replace by d square delta dt square. That means, your this equation can be written as m d square delta dt square is equal to p I minus p e. So, using equation 16 and equation 6. So, if you equation 6 means that m is equal to, in equation 6 m is equal to g h upon pi f, m is equal to g h upon pi f, that is in equation 6. So, put it here d square delta by dt square is equal to p I minus p, that is it is megawatt. So, we are taking the real unit of m, not divided by g here. So, dividing, if you divide this throughout by g, the MVA rating of the machine, that means what will happen, that divide by g. So, if you divide by that, actually MVA rating of the machine means it is its own base. So, you can write MPU is into d square delta dt square, and if you divide by g, the machine base, megawatt will convert it to per unit. So, m per unit d square delta dt square is equal to p I minus p, that is equation 18. So, where m per unit we have seen h by pi f, we have seen it before. Therefore, h upon pi f this into d square delta dt square is equal to p I minus p, wherever is possible I have written, wherever megawatt or per unit, here it is per unit. So, this equation actually is called the swing equation. It describes the rotor dynamics for a synchronous machine. This is swing equation, and it describes the rotor dynamics of the synchronous machine. So, once it is done, then what we will do, let us come to the multi machine system. Look, multi machine system transient stability we will not study in this class, that is basically for postgraduate student, and multi machine system transient stability we cannot solve numerical in the classroom, because one has to follow the iterative technique. So, why I have written multi machine system means we want to just find out the equivalent inertia constant, that H eq. So, that is why multi machine system, but we will not study the transient stability analysis of multi machine system. So, in a multi machine system a common system base must be selected. So, for example, earlier we are doing G and H, but what we will do, instead of G we will write G machine is equal to machine rating, that is base value, and G system is equal to system base. So, equation 20 then can be written as, that means this equation instead of H I am putting H machine, but H and H machine it is same, just is a multi machine system. So, we have to make it machine 1, machine 2 like this, but H machine and H both are same. So, this equation we can write this equation 20 we can write, that is H machine into divided by pi f, into d square delta by dt square is equal to P I minus P E. So, that is this equation. Now, if you multiply both sides by say G machine, that is the machine rating, then G machine, this equation I have written here for your understanding, and because this is in per unit, but if I multiply the G machine, the machine rating base. So, G machine into H machine into d square delta dt square is equal to P I minus P into G machine. At that time it is converted to megawatt, that is why I have written here megawatt, right. So, now that whole thing, this whole equation, now you divide by the system base. Suppose you have taken say G system a different base. So, divided by G system, this whole equation you divide by G system, that is system base, this equation. If you do so, it will become G machine upon G system, G machine upon G system into H machine d square delta dt square, H machine your here I have missed one thing, that is your what you call that pi f term I have missed, right. So, so this pi f was missing here. So, now I have written. So, into d square delta dt square is equal to that H machine upon pi f d square dt square is equal to P I minus P into G machine by G system. This is equation 21. So, everything is same, but we have a different base now. So, H system by pi f into then d square by delta square, that means this thing your what you call whatever here you have in terms of that pi f is there, but other thing G machine into H machine upon G system, we will write that one is H system. So, we are writing something H system upon pi f into d square delta dt square is equal to P I minus P per unit on system base. That means, P I minus P and G machine upon G system. So, we are writing it is per unit on system base, this is per unit on system base, because G machine upon G system. So, H system is equal to G machine H machine upon G system. So, H system is equal to G machine H machine divided by G system, that is system base, that is 23. So, that means, this is machine inertia constant in system base. So, this is required actually when you try to find out that equivalent inertia of the your machine for a multi machine system. And for a multi machine system, that when a group of generators they operate in parallel, they swing in unison, I mean they are in coherent group, that means their increase or decrease of the speed will be same. So, that means there will be in coherent group, sometimes we call coherency. So, that will we will come back to that. Thank you.